Now, how can we use the central limit theorem to answer sensible questions? We saw one question we just answered. Another question that's very often asked is, how big a sample do I need? And the answer, of course, is for what? But let's look at one situation where we can answer this question. And so here's our population. Now, suppose we don't know, as is always the case, or usually the case, sorry, as is usually the case, we don't know what the population is, and we're going to take a sample. So the question might be phrased this way. How big a sample do we need to be 95% sure that the sample mean for total cholesterol level is within plus or minus 25 milligrams per 100 milliliters of the population mean? And you can see the way the question is phrased. We have to inject a certain amount of uncertainty. We're never certain. As we said right from the start, we're never certain. We've got a level of uncertainty. So here, let's use the ubiquitous 95%. So how big a sample do we need to be 95% sure? So I'm not going to be certain, but I'll be 95% sure that we will be within 25 units of the population mean. So our sample mean would be within 25 units of the population mean. It means I don't know what the population mean is, and I'm not certain that what I'm going to do will be within that limit that you've set, but I'll be 95% sure. That's the best I can do. So what we want is the probability that the distance or the difference between our sample mean and the population mean is between minus 25 and 25, and we want to be 95% sure of that statement. So let's standardize, divide by the standard deviation of the sample mean or the standard error, which, because we know the population standard deviation, I'm being a little bit fake here. I'm acting as if I know the population standard deviation. I realize that. We'll remove that shortly. So, but let's just answer this question. So divide through by the standard error. And why do we do that? Well, we do that because then, what does this look like? That's just our standardized Z. So what we're asking is, what is the probability that Z will be between minus this quantity and plus this quantity? We want that to be 0.95. So we know with a standard Z, it's between minus 1.96 and 1.96 95% of the time. So what we'll want is for, let me clear it out. So what we want is this quantity to be minus 1.96 and this one to be plus 1.96. And in order to do that, we can solve, because n is the only unknown in here, we can solve for n, and it turns out that n of, well, we can't have a fraction of an n, so let's just round it off. So an n of 13 will allow us to be 95% sure that we are within plus or minus 25 units of the population mean by using the sample mean. Suppose we want to lower that 25 to, let's have it to 12.5, then what we would need is 50. So 49 will almost get us there, but 50. So we need a sample size 50 to be 95% sure that we will be within 25 units. I'm sorry, 12.5 units of the population mean. Not certain, but 95% sure that we're doing the right thing. So here it is in summary. We want to be 95% sure that we're within plus or minus delta, then we need a sample of size n equals this quantity, where sigma is the population standard deviation. So this makes sense. The bigger is our sigma, the more variable is our population, and we've been saying all along, the less homogeneous it is, then the bigger the sample we're going to need. And the smaller we make delta, the more precise you want to be, then the larger your sample size. So those are the two controlling factors here. How close do you want to be? And how variable is your population?